Our next speaker is Cumrun Vafa. We'll talk about topological and superstrings at large n.
It's a pleasure to give a talk here. I'm going to talk about these two works, work with Mina Aganagic and also Mina and Marcus Marino. So this is going to be the main part of the talk. Related talks that you will hear later by Hiroshi Oguri and Robert Dycraft later is connected partly to what I will explain the connections. And also more directly connected to the talk I'm giving here is the nice work done by Diaconescu, Flori, and Grassi. This is a kind of a short map of these connections. It's a bit overwhelming. We have only so short amount of time, so squeeze it into short transparencies, I guess. So this is a quick summary of some aspects of topological strings on Calabi-Yau threefolds. There are two versions of this, what's called the A and the B version, which are related to each other by mirror symmetry on the Calabi-Yau. And each one of them have two different versions, subversions, one open and closed versions. The open string version means we put D branes in these cases, closed means we don't, the same with the B version. Everything we say here by mirror symmetry will have an equivalent statement on the right side, so maybe we'll first talk about left side. The A side, topological strings, corresponds to, in the closed string side, corresponds to some kind of a gravity, could be called Kähler gravity, and this basically counts holomorphic curves, namely holomorphic maps from Riemann surfaces to target space geometry. The open string side computes Chern-Simons theory on some three manifolds. So Chern-Simons theory on three manifolds related to open string version, and closed string version counts holomorphic curves. Typically, gauge theory things are easier than gravity things, so this is also true here. This is typically easier to study or compute than the gravity side. The B version, there is the open again and the closed version. The open version, open string version, has some holomorphic version of Chern-Simon, and in some cases it reduces to matrix models. This would be subject of Robert Dycraft's talk. And the closed string version is a kind of a gravity called Kodaira-Spencer gravity, which can also be viewed as quantum version of special geometry that Calabi-Yau threefolds enjoy. Large N duality connects the open and the closed strings together. A proof of this in the context of Chern-Simon on three-sphere will be given by Hiroshi in his talk using the worksheet derivation. And there's similarly, of course, the large N duality which connects this side, so matrix models computes the closed string answers on the other side. There's also a relation with four-dimensional superstring compactification to 4 dimensions. So the A side nicely goes to type 2A string, and the B side goes to type 2B strings. So in particular, the open side descends down to n equals to 1 supersymmetric gauge theories in 4 dimensions. And the closed string side descends to n equal to 2 supersymmetric theories, which are broken to n equals to 1 by some flux. And similarly, of course, by symmetry here. And the connection between them is the topological string computes F terms in the corresponding gauge theory. So supersymmetric theories have typically some nice pieces, holomorphic pieces, like superpotentials and so forth, which can be captured by these topological string computations. Direct computation of genus G topological string amplitudes has been very difficult. For small genus, there has been some success using either mirror symmetry or using mathematical localization techniques. So these in principle can be used to compute FG, even though the technique really gets difficult for larger Gs. For small G, it has been practically applicable, and people have computed them using either of these methods. And the question would be how to compute the all genus version of these amplitudes. So the aim of my talk is consider a model and use the Largent duality between open string and closed strings to start with the open string side to compute the closed string amplitudes to all genus. So what is closed string compute in the A model? Well, if you typically it's a function of parameters, scalar parameters, which I denote T, the sizes, scalar classes of the Calabi-Yau, and lambda being the string coupling constant. So there's an expansion in genus G expansion for the partition function, and the genus G computation, fg of T, computes holomorphic maps from genus G Riemann surfaces to Calabi-Yau, where T denotes the areas of the corresponding curve. So each curve contributes some amount by e to the minus the corresponding area, which in turn is a function of these scalar parameters. And this is I guess I should put in quotes, it's kind of counts maps from holomorphic maps from Riemann surfaces to Calabi-Yau. A more precise definition of the counts is the Gromov-Witten invariance that's well studied. It turns out that by some string connection with string theory dualities, it's easy to show that this can actually be written in this form. So there's not arbitrary functions appear here. Functions that appear here, the T lambda dependence should combine to give this structure, and the whole thing can be captured by some integers which physically count the number of BPS states of charge D with spin S. So what this means is that if you take M theory on the corresponding Calabi-Yau threefold and you take M2 branes, the charge of the M2 brane depends on which class in Calabi-Yau they are wrapping, and they have a 5-dimensional spin. The SU2 part of an SO4 in the 5-dimensional spin is what is computed by the S, which is captured by the G dependence here. So the whole thing boils down, this complicated thing boils down actually to another complicated thing, which is computing these integers, a doubly infinite series in spin and also these classes. Counting of those, for example, will have properties, for example, predicted by Beckenstein-Hawking formula about these growths. So these are interesting numbers for black holes, for example. So I first have to recall what is the Chern-Simon topological string duality. So we take n D branes in this topological A model. So in the topological A model, the open string corresponds to D branes wrapping special Lagrangian submanifolds. So take the deformed conifold. It is topologically cotangent of S3. And there's a special Lagrangian three-sphere at the apex of the cone, which is resolved to finite size and deformed to finite size. And we wrap n D branes around there. And this gives rise on the target space to open string field theory, which in this case is exactly the UN Chern-Simon strings on S3. UN Chern-Simon field theory on S3. So that's the left side, the gauge theory side. The gravity side computes the topological strings on resolved conifold, where the size of the conifold, the resolution size, is proportional to this n times the string coupling constant. It's equal to n times the string coupling constant. This is the 't Hooft parameter of the corresponding Chern-Simon theory, and it's similar to the other ADS-CFT, for example, dualities, where the size gets related to the 't Hooft parameter, the size of the spheres and so forth. Again, of course, we have gotten rid of the D brane on the right side. It's closed string only. So the statement is that the UN Chern-Simon on a three-sphere is equivalent to topological string, the A model on this geometry, which has a compact two-sphere P1 on two non-compact directions, O-1 plus O-1 bundles, so two spin bundles on top of P1. In that case, the answer for topological string can be computed in both ways directly. You can compute the gravity size, which turns out to be easy also. So you can study this and you can study this directly. In this case, it's kind of easy because you only have a two-sphere. The only M2 brane can wrap that two-sphere, and there's only one. So the n's that I was talking about in that case is just for the wrapping number of the P1 being 1, with spin 0, that's 1, and the rest are 0. So that whole computation boils down to just one non-trivial answer, and the rest are 0. So it's kind of boring in that sense from the closed string side. But nevertheless, it can be checked directly that it agrees with the corresponding UN Chern-Simons on S3, whose answers also can be done using the connection that Witten discovered between Chern-Simon's theory and rational conformal field theories, in this case the WZW models. So both agree with this. Conifold transition has a dual description in terms of type 2B PQ5 branes, which at least allows drawing the pictures easier in this context, which I will use. So I won't, strictly speaking, use the duality too much except for motivating drawing pictures, which makes the geometry easier to describe. So if you think about PQ5 branes, if you take, for example, M theory on Calabi-Yau threefold, you can replace a local Calabi-Yau, it turns out, by a dual description of type 2B with some collection of PQ5 branes. So for example, if you take 0, 1, and 1, 0, 5 branes displaced in some orthogonal direction, it turns out that this corresponds to the conifold. It's dual to the conifold, deformed conifold where you have this S3 going from the closest points between these two branes. The transition, the conifold transition, the resolution is basically bringing these lines together and then resolving it this way, so you get a 1, 1, 1, 5 brane in the middle. And there are two ways you can do it. You get 1, 1 or 1 minus 1, depending on which way you go. And these are what's called flops. So the two ways of resolving the conifold is basically this picture that you go down and you can deform this way. So of course it's geometrically very easy to appreciate that. It might be more difficult in terms of algebraic geometry to see this, but it's also equivalent to that. So that's the local symmetry that we're talking about, Largent duality. So the question is how to use this Largent duality to compute the topological string amplitudes on much more complicated threefolds. We again consider non-compact threefolds, which have things more difficult than P1. For example, P2, four-dimensional objects, or for example, P1 times P1. More general, we can consider things, a well-studied class, which is, for example, toric threefolds, local models for the local Calabi-Yaus, which come up in geometrically engineering n equal to gauge theories in particular. So the question is, can we compute these in those contexts using this duality? Now, however, to begin with, you think this might be too difficult or impossible because, after all, in these cases, there are there are infinitely many non-trivial classes you can have. For example, you can have arbitrary degree curves in P2 and the same in P1 times P1. So you expect that these numbers, the number of BPS states of some charge D and some spin G, is infinite is non-zero for infinitely many D and G. So that seems like these are much more complicated than this Largent duality we talked about. Unlike the P1 case where only one of them was non-trivial. So it might be impossible to get it. For example, let me talk about P1 times P1 in a Calabi-Yau. I draw the picture in terms of the PQ5 brane because it's easier to appreciate. So you can take a collection of the PQ5 branes in this form, where I have labeled the PQ version of the 5 branes. So this collection of PQ5 brane is dual to local Calabi-Yau models on P1 times P1. And the connection is basically that you view the Calabi-Yau with the circle fibration, S1 times S1 fibration, and you basically look at where the circle fibration degenerates, which PQ cycle it degenerates, and you read off what PQ fibrane you put. That's the duality, basically. And then you have the strings, PQ strings, which can end on these 5 branes, and in this way, these strings that we talk about here are precisely these things that we're counting in terms of M2 branes. They lift up to membranes in the M theory, and these are the things that we were counting, these integers. So we want to count how many bound states, for example, you would have of these strings ending on 5 branes. So that's a physical question we want to understand in this language. And remember, the connection to P1 times P1 is perhaps more familiar in the context of remembering the connection between the interval and the P1, where if you look at the circle action on a P1, which is just this fibration of this P1 with the circle, there's two endpoints, the north and the south pole, and that maps to the interval. So you can see the two P1s here basically by the fact that you have a rectangle here. And there are some non-compact directions that are also these, and also something coming out of the figure, which gives you the threefold description. So this is a P1 times P1 in a Calabi-Yau, and as you can see, there are infinitely many charged things because you can do arbitrary complicated webs here. So it's a complicated thing to study. If you had the single P1, you couldn't do it, and that was the simplicity of the previous one. But if you have two of them, as you can see, there's much more complicated things, and the question is, how do we count these? So that's an equivalent motivation from the physics language of the question we're asking, counting these guys. instead of the P1 times P1, let's consider a similar problem, in fact, extension of this problem. So the P1 times P1 I draw was this kind of collection of 5 branes, but you can actually include some other things. You include these 4 extra 2 spheres in this collection. So this corresponds to blowing up some blow-ups that you do in this P1 times P1 geometry, and so it's kind of a related model, but it's a bigger model. As you can see, if the size of these spheres are big, the size corresponds to the size of that interval. If the size of the interval is big, you get back the P1 times P1 piece, that green, the rectangle inside the green curve that I've drawn there. But this is a more difficult model in the sense there's more things that you could compute. So the idea is the following then. Each of these other S2s that I just introduced can be a point I can apply the duality that I deal with in the following way. Suppose we shrink these 4 S2s to nothing, to 0 size. In this case, the picture looks a very simple one. So you have 2 105 branes and 2 015 branes. And then you can lift off the 2 105 branes in one direction off, and you get 4 3 spheres, like that. So then the idea would be to put D branes on each of these 4 3 spheres, N1, N2, N3, and 4 D branes here, and use the local duality of S3 to S2 locally on each one of these. And then take N goes to infinity limit, because the size of the S2 is proportional to N. Take N to infinity, strictly equal to infinity, and you're going to be left with P1 times P1. So the idea is basically taking the Largent duality locally in the geometry, but get rid of it at the end. At the end, push this geometry off and get the answer for just this little piece inside. So this is like these dropstick games if you played with it. So you just lift it off 2 of these lines, and you can put in these branes around N1, N2, N3, N4. So if you wrap ND branes around these guys, N1, N2, N3, N4, then you get the product of UN1, UN2, UN3, UN4 Chern-Simon on 4 different 3 spheres. But you have something more. You have bifundamental matter between them. But bifundamental matter is very simple in this case. There are just basically 4 of them between these, on the sides of these rectangle. And it turns out that you can integrate them out. It's a massive thing. You can integrate them out and find what the effect is in terms of observables of the corresponding Chern-Simon theory. It turns out when you integrate it out, it's 1 loop exact, it turns out. So you just get the annulus contribution, very simple. And the annulus that you get is basically the fattening of this line to an annulus here. So this basically gets promoted to an annulus. And the ending circle on the corresponding S3s have the geometry of knotted circles, the Hopf-Link. The computation of the Chern-Simon invariant for the Hopf-Link is well known from old days, again by work of Ed, which gives you the modular transformation matrix of the WZW characters. So you take the character of UN gauge theories and the modular transformation, tau goes to -1 over tau, gives you a matrix. The computation of the Chern-Simon with some knot invariance is doable basically by computing that S matrix, which is well known. So P1 times P1 boils down to 4 Chern-Simon theory with 4 Hopf-Links paired up in that way. And the annulus basically tells you that whatever representation you put here, you put over there. So that's the linking connection when you do the 1 loop computation. And there's a propagator which comes from just doing the Schrödinger computation, which is e to the mass roughly times the length. So T is the mass, and the mass T is the length, and the mass turns out to be the number of boxes in the Young tableau. So it's e to the minus a propagator kind of. So you basically end up in a very simple form. The full topological string answer to all orders is just given by this simple trace, where this S is this modular transformation matrix I talked about. These are the propagator UT. There are 2 different scalar parameters, T and T prime. And so it's a relatively simple structure here. And you have so you go around like S, the transformation here, you propagate by U. You do S transformation again, you propagate by T prime. You do S and so forth. So going around this, you can actually get such an answer, and you trace it because you end up with the same representation here. So, so that's the answer. So so this whole genus computation finished. It's basically in this form. Well, it's finished, but can we check it? So the Largen duality says that this P1 times P1 with 4 extra P1s, these 4, is equal to doing this trace computation in the collection of these Chern-Simon theories, where there are 4 different groups, UN1, UN2, UN3, UN4, with the corresponding S's glued in this way. How to get P1 times P1? Well, as we said, we have to take Ti's to infinity strictly. We have to get rid of n, so strictly n equals to infinity limit. But you get rid of these guys, but you keep the P1 times P1 finite. More precisely, it turns out there's a renormalization of these T's, so we have to be a bit careful. So the renormalized parameters that you have to keep is this combination of the T's. So for example, if you take this T parameter, the thing that you end up want to keep finite is T minus the sum of these divided by 2. So we want to take Ti's to infinity and this T to infinity in such a way that this combination is finite. This sounds a lot like the kind of things we had seen long ago, at least some older ones among us had seen a long time ago in the context of the double scaling limit of these matrix models, which one strictly took n to infinity and some other things, tuned some parameters in it to get some interesting answer. That's what we're doing here. We're taking n strictly to infinity, but we're choosing the geometry or the interactions in the matrix model analog to be finite, in some sense, leftover, tuning it, which gives you the leftover parameters of P1 times P1. Similarly, for P2, the story is similar. Instead of the rectangle, we have a triangle. Looks like Euclidean geometry we're doing. Again, it's convenient to introduce 3 extra P1s so that this whole thing looks like 3 drop-sticks on top of each other. So we can then lift up, so this you have, like, let's say 1, 0 brane, a 0, 1 brane, and a 1, 1 brane, 5 brane. And you can actually move them off of each other. That's the transition of S2 shrinking and S3 is growing. In this case, the duality states that this computation boils down to the computation of this modular transformation matrix S, and you also end up with this other modular transformation matrix T, which corresponds to tau goes to tau plus 1 for the WZW model. So the statement is that that computation should be equal to this. Now, what we have to do to check this, well, we have to, strictly speaking, take this computation, which is known what to do for any given n, take the n1, n2, and n3 to infinity, tuning the propagator's lengths appropriately, and extract the numbers as a function of t. This should give us the answers for topological strings on P2. Well, so again, this is what I just said in words. So we want to take these 3 sides to infinity to be left just with the triangle P2 in the middle. And so you want to take n1, n2, and n3 to infinity, fixing this combination. Well, so this can be done, especially if you have very powerful people working with you. So what are these? So this is the computation for P2. So let me say it in the language of M theory, maybe, that more motivation. Take M theory on a 3-fold, which has a P2. You want to know how many M2 branes are there, bound states are there, of a given charge. There's a 2-cycle they can wrap around. So that's D. And there's a spin. There's a BPS spin, which has to do with the SU2 that is preserved for the SO4 rotation. So you can ask, with a given spin of given charge, how many are there? Okay, that's a physical question. And topological string connection allows you to compute it and you get these numbers. The fact that these come out to be integers is highly non-trivial. It was not a priori guaranteed that the Chern-Simon sees this integrality. So that's already a first check, that they come up in the integer expansion as they should have. So this is from degree 1 up to degree 8. So the first few genus, 1, 2, 3, and maybe I don't know, 4 or 5, some of these were known. Genus 0, of course, was exactly known for all D by using mirror symmetry. And some genus similarly by mirror symmetry and similar techniques, and also in a different way by localization. Some of these lower ones were known. The full answer for all of these was not known in the description I've given, so this goes, well, further down. Degree 11 and 12 and so on and so forth. So you can actually compute. This is exactly computable. It's a practical method. I want to emphasize to compute it also, not just theoretically equivalence. And, well, try checking that number by direct method or any other method. Similarly, you can do it for P1 times P1. Again, now here you have two charges because the M2 membrane can wrap around two different P1s, so you have different charges, but then different spins, and you can do similar computations by these expansions. Well, now that we did P1 times P1, nothing prevents us from extending this. You can take, for example, a lattice of PQ5 branes. For example, the simple lattice here is just this rectangular lattice. And basically, you think of these as dropsticks, and you can lift them up and down. And so you can put S3s wherever they come close to each other, and use the Largent duality to describe some A-model dual, whichever version limit you want to take. So a certain double scaling limit of these will give you topological strings on all local Calabi-Yau threefolds. So that's a full answer for Calabi-Yau threefolds in the A model. You can embed this in superstrings, of course, as I said. So the way you think about that is that you take the Calabi-Yau threefold and times R4, and you think about D branes instead of 3 dimensions, D6 branes filling the space-time. So you have N1 D6, N2 D6, N3 D6, and N4 D6 brane. So the dualities I told you about directly descend to duality for superstrings, where the D branes are replaced by fluxes, N1, N2, N3, N4, and these correspond to gauge condensates. So what is the double scaling limit? The double scaling limit corresponds to taking n's to infinity, which corresponds, since the total flux was finite, it corresponds to having a Ramon flux go to 0 per unit volume. So effectively, we are getting dualities of large n with gauge theories for which the closed string site has no Ramon flux at the end of the day. Nevertheless, the geometry of the Calabi-Yau is not trivial like R10 or whatever. It has interesting geometry. So you can end up, in the superstring terminology, the meaning of double scaling is there are large n dualities, gauge theory, and string theory for which there are no Ramon fluxes at the end, but the superstring geometry is not trivial like R10. There's some interesting geometry left over, like P1 times P1. And you can do this in many other examples. So to summarize, this is the significance of double scaling limit, superstring gauge theory dualities for which the RR flux is 0. I'll stop here.
Most people ask questions should identify themselves and their institution.
Okay. Using the similar idea, can you calculate? This is Jamal Park from the Pohang University of Science and Technology. And my question is, using the similar idea, is can you calculate the open string Gromf-Witten invariance of the higher genus?
Yes. I didn't mention this, but for example, we applied this technique to compute. For example, if you take P2, you can put an open brane here, for example. So yes, you can compute these, and we have computed and checked it against known results, and it agrees.
Hi, Mike Douglas from Rutgers. This is great. You can count curves, say, on P2. Can you count bundles on P2, things that wrap the P2?
So the question is, can we compute bundles? That motivation of that is, again, can be, of course, motivated by D4 branes, and D4 branes bound state instead of D2 branes and P2. And specifically for P2, we don't know. For specific cases like P2 bound about 9 points, we can, by the fact that that is elliptic. And if it's elliptic, you can use a duality which maps D2 branes to D4 branes. So you can map backwards D4 branes to D2 branes and compute it. So in principle, you should be able to compute also P2 by blowing down. So if you know the answer for P2 bound at 9 points, you should in principle be able to blow down. But that has not been done in detail.
Okay. Thanks again.